object in a gas, on the average, had the same kinetic energy. Granted that any one particle could sometimes be going slow, sometimes be going fast, but there was an average. And at a given temperature, everybody had the same average energy. It also turned out that this would be true if you had a box like this. So Planck imagined that this box is made up of individual little oscillators. This is a very rough picture, but you know, if you make a rough picture, you should be able to get at least a rough answer. So he imagined that you have oscillators which make up the box. And each of these oscillators should have a certain amount of energy. As I increase the temperature, regardless of the frequency of these oscillators, have all different kinds of oscillators, different frequencies of these. It's a little bit strange model, but it turns out to be a workable model, so you do it. He said that each of these oscillators in here should have the same average energy, half mv squared, proportional to kT. Actually, there's a factor of 2 in here for each. So each vibration, or each oscillator, even its potential energy, half kx squared, will also, it turns out in theory, have the same energy. So every oscillator will have the same energy. And that would mean that the difficulty that comes in is that if everybody has the same energy, if you have a very, very large number of oscillators, and everybody has kT of energy, you have a tremendous amount of energy in this box, in the walls of the box. In the limit that you have an infinite number of oscillators, you say the box has an infinite amount of energy, each particle in it, each oscillator in it, having kT of energy. This is, again, this idea of equipartition, that every entity in the box has the same energy, and if you have an infinite number, they will give you an infinite energy. And that sort of violates our feeling that it shouldn't be possible that a thing has infinite energy just because it gets larger, that the energy could be infinite. The analogy that Richard Feynman came up with was something like this. If you had, let's say, a campfire, I think of the campfire as being a black body at a certain hot temperature. There's radiation coming out of there. Now, if every wavelength had the same energy, that means not only should you get red light, blue light out of the fire, you should get every wavelength should have the kT of energy, which means that even if you had X-rays having kT of energy, you would have X-rays coming out of the bonfire, which doesn't happen. When we see it doesn't happen. At high enough frequencies, the energy goes down. So there's a cutoff sort of the wavelengths that come out. So if you look at a bonfire at a certain temperature, like a 1,000 degrees or a few thousand degrees, where the white light is coming out, we don't get X-rays, we don't get frequencies all the way out here. So they get cut off. But theory says every wavelength should have the same energy, equally partitioned. Everybody has the same. So Planck had to solve this problem. Why does the spectrum cut off like that? It seemed like a pretty simple thing, but it was a big puzzle in those days because people were pretty confident that everything should have the same energy, equipartition, meaning every part has the same energy. So I give you the analogy, it's in my notes. It's a really grisly analogy. The why it is, how it's possible that the idea of a quantum of energy solves the problem. And this is where Planck came up with his idea of the quantum. Well, how does the quantum solve this idea? So the idea is that suppose you have, like, instead of an infinite number of oscillators in a box, you have an infinite number of people, and you're trying to feed them all. If you give everybody the same portion, equal partition, give everybody the same portion, if you have an infinite number of people, you're going to need an infinite amount of food. Okay, and that's impossible. So you don't want to do that. But everybody, okay, now suppose we have, we would call that this idea that you would have an infinite amount of energy means that this curve keeps going up and up forever, and we call that the ultraviolet catastrophe. This is what it was called at the time. Meaning that if every mode was possible, that this would keep going up and up and it wouldn't cut off, and you'd need an infinite amount of energy. So here we call the, in my analogy here, if everyone gets the same amount of food and can survive, we call that the ultra-age catastrophe because we have people of all ages and they're all eating and they're all taking food and they're going to need an infinite amount of food, which we say we don't have. Okay, but we have a quantum solution, which is not pleasant. Namely, we're going to say, rather than everybody surviving, as a person gets older, we'll say that he needs more food. So there's a quantum of food depending on how many birthdays you've had. So we draw a picture like maybe I'll do it here. See if so we have young people, we have a little bit older people, we have a little bit older people, we have a little bit older, and yet older. So this is the frequency of their birthdays, how many birthdays they've had. And we're going to give everybody the same equal portion of a ration. Say this much. Now the point is that if you give everybody this person's okay. This person's okay. This person, well, yeah, maybe. You're giving them a ration of kT of energy or food, and maybe he's okay because he gets a little bit. This person is in trouble because he's getting not a very good ration. This person, given only this ration of energy, kT, is maybe not survive. So he'll die off altogether. So what happens is that if there's a quantum of energy or food needed, you're going to kill off the old people or the high frequency waves. So that's what's going to happen here. Here, you see we have low frequency oscillations, and they require a certain energy. If suppose I'm putting in an amount of energy kT about like this, these fellows will survive. They will be okay. But the ones out here requiring more energy, they will simply die out, and you will not excite them. And the ones out here, even worse, see that they're only given this much kT, and they need much more, and so those will simply not get excited. Occasionally, a little bit, a little bit. So like that occasional kick that somebody had. So that's the idea. This dying off of the thing, we actually have a phrase in physics, of freezing out something. You can freeze out certain oscillations. By lowering the temperature, you lower how much you're providing to these things. And so some energy level like this one, if I lowered the temperature and provided this much energy at a lower temperature, it would eventually freeze out. So if I provide this much energy instead of this much, lower kT, this oscillation will stop oscillating because it doesn't have enough energy. So we speak of freeze out. In other words, lowering the temperature, you will freeze out certain oscillations. So that's why this curve ends up the way it does, by the quantum idea. Namely, that Planck said the only way to get this curve is to say those high frequency oscillations require more energy to get going. And if you don't provide, if the temperature is too low, they simply won't oscillate, and they won't absorb any energy because the oscillator is an all or nothing thing. You have to give it enough or else it simply won't get going. So that's the quantum solution. You can read that. I don't know if you like the idea, but it's the one analogy I can think of. And that's the point is here, if you have low-frequency oscillations, the energy separation is, say, this much, and kT is enough to excite these kinds of low-frequency oscillations. On the other hand, the same kT, if you have this much energy needed to get going, if you put in kT less than that, the oscillation doesn't get going and sort of dies out. So that's a physical explanation of why quantum levels, energy levels, were introduced into physics. That an oscillator doesn't just oscillate at any frequency, it oscillates in multiples of frequencies and not in between, and you have to give it enough energy to get up to that, or else it doesn't get going at all. So that's the idea of the quantum level. Now, oh, I'm sorry, I want to go this way. In my notes here, I point out that headlights have to do with this, namely, the higher your temperature, in other words, 3,000 Kelvin, which is where some headlights run, you have a certain amount of blue light and a certain amount of red, and if you can shift the temperature higher, you get a little bluer headlights. Okay, that's nice. But the sun also acts as a black body, roughly, and this is the actual spectrum. And I think maybe this is the spectrum that arrives at the Earth's surface because the atmosphere absorbs some. But as I showed you, it's pretty much right where our eyes are sensitive, the red and blue sensitivity of our eye. Now, this phenomenon is very important for understanding the greenhouse effect. Everybody worries about the global warming. This is what's behind global warming. First of all, at the temperature that we're at, roughly 300 Kelvin, we radiate at a very different wavelength. At about it's about 10 microns or so, which is very much longer wavelength than the sun's radiation. And the consequence of that, and so other things in our world, not only we, but the tables and the trees and the sidewalks and the roofs, radiate in this spectrum here, about this wavelength. So what happens? Well, the light that comes in from the sun comes down and it's in this frequency range, very high frequency, short wavelength. But the outgoing radiation is in this spectral range, namely around 300 Kelvin. So if you look at what the atmosphere absorbs, it's a miracle. But our atmosphere of oxygen and nitrogen, this is the transmission. It's almost 100% where the light's coming in. That's truly a miracle. Our atmosphere allows sunlight through to about 90%. Imagine if it were opaque. The sunlight would not reach the surface of the Earth if our atmosphere were absorbing. But it's a miraculous thing that the transmission is given by this. Where if I can find the arrow again. Yeah. See, this is the transmission, and it's like 90% right up in here. But in the range of frequencies where we are radiating back to the atmosphere, after it warms the Earth, and the Earth goes to about 300 Kelvin, there are all kinds of absorption. So the transmission gets very poor. And these are the various gases. I can't read it off this thing, but there's carbon dioxide is one of these things. Even water vapor is very strongly absorbing in this band. So the band that we're radiating back out is absorbed strongly in the atmosphere, and so it doesn't get out. And that's the global greenhouse effect. Namely that if these absorptions are strong, the light doesn't get out. And so it's a good thing in a way, it keeps us warm, because if the light all this radiation got out, we'd probably freeze at night. So you do want some kind of a blanket, which is keeping the radiation in. But the problem that people have is that some of these bands are getting so intense that we're heating the atmosphere too much. And the reason is that what's happened is there's a shift of where the light coming in passes through, and the light going out is more or less blocked by molecular absorptions, like carbon dioxide and oxygen and water vapor. So black body radiation is really what they talk about when they talk about global warming and the carbon dioxide problem. Restricting carbon. Why restricting carbon? Is because it's absorbing in the region where we are emitting. Okay, well, there's a couple of other little stories here. I want to move on. I hope that's some clarification, a little understanding of why the black body was important and how we explained it, plunked it, by assuming that there were energy levels, distinct energy levels, and that thermal energy was not enough to excite the high frequency ones, and therefore they would cut off. I want to show you there's another nice, I can get it, demonstration. Oh, tell you what, I've got this thing set up here. Let me skip to this. The other key discovery, first of all, was these quantum levels, which was a big discovery. Not at all obvious. The other great discovery was the fact that material particles, masses, have a wavelength associated with them. This was postulated by a French physicist around 1924, 900 years, where the wavelength is given by, well, T is H over md. No, wait a second. This is what it is. The momentum of a particle is associated with a wavelength. Now, this is a very important idea, and it solved the question is, where do these quantized levels come from? And what it's going to turn out is it comes from the fact that we have standing waves, where a wave comes back and sits upon itself and gives you a nice harmonic, as it were, sort of like a musical instrument. If the wavelength is matched to the size of the instrument, it builds up and it gives you a standing wave. That idea was important. I just wanted to show you the demonstration of that. Well, we've got it set up here. Let's skip to this. Namely, what we're going to do here is this is the old-fashioned cathode ray tube. Way back yonder in the back of this is a source of electrons. We have a voltage screen, which is accelerating this to 10,000 volts. So those electrons are being speeded up. They are going to be passing through a sheet of graphite, carbon, which has a periodic structure. And because the electrons have this wavelength, this will act like a diffraction grating, and the electrons will be deviated from their path, straight path, and they're going to cause spots, sort of like the way your lines appeared in the diffraction grating. So the solid material will act as a diffraction grating for these matter waves. These are electrons coming out of here. So let me try to, let's hope it's clear enough. There you go. See these rings? Because the graphite is in every which direction, the electrons coming through are diffracted and produce rings and spots, which is a diffraction pattern due to the wave nature of the electrons. I have in my notes a picture of a similar thing where we have a similar pattern produced by X-rays. X-rays we know to be waves, believe them to be waves, and let me maybe go back to my, this popped up. Let me put this away for the time being and go back to this one. Let me run ahead to this one. This is a picture. Oh, I got to put it back to here. Oh no, I didn't mean to do that. Oh, I pushed the wrong button. Oh. Yeah, where you get the same material, where we shine X-rays through it on one side, on the left, and we have an electron beam passing through the same material, and it shows that you get similar ring-like diffraction patterns from both an acknowledged wave, namely X-rays, and these waves which are matter. In my notes, I get a little bit greedy and show you an experiment that I did myself years ago, where, this is very impressive, you should know about this, you can take a single molecular layer of oil floating on water. It's an amphiphilic thing, it's a paraffin chain with an oxygen end, similar like a biological membrane, and you can float it on water, like this. You have a whole bunch of these molecules floating on water. If you put a plate into the water and pull it out, the molecules, the ionic end will stick to the plate like a quartz plate, and you can pull the molecule off and you get a one monolayer structure with your own two hands. It's really cute. It's called a Langmuir logic film. Have you anyone come across it yet? No. Well, it's very nice, and you can pull repeatedly. If I can get this thing back again, you can repeat that and get one layer, and then when you push it back in, the oily ends stick to each other. Oils stick to oils, and you can repeat this and get this multi-layer structure. So actually, what happened was one year I went to Oak Ridge to give a talk about this process of Langmuir films, and it turns out that at Oak Ridge they have a nuclear pile where they make neutrons on demand. So I said, well, neutrons, they're nice, they're little particles, they have a wavelength. Why don't we shine wavelength neutrons on my little films and see if I get a diffraction pattern? Matter on a periodic structure to see if you can get a diffraction pattern. So I'm using the wave nature of neutrons to do that. So, of course, I had done before with my collaborators I was working at IBM at the time, we had done X-ray diffraction. And here at a very low angle, you shine in X-rays on these films, and you get these diffraction peaks when one layer sends out a wave, and another layer has a different path length, so it sends out a wave, and you can get these strong interference peaks, very powerful. This is logarithmic scale. These are huge, sharp peaks from these beautiful films. So I said, well, let's try this with neutrons. And they did. And sure enough, again, at low angles, you get these nice, strong, well, this is the theory. The actual experiment of the dots, which is not perfectly fitting, but pretty good. And so the point is that matter has a wavelength, and you can use it, just like a regular wave, to get interference and diffraction patterns. This is the breakthrough idea that we'll exploit the next time and understand all kinds of atomic phenomena.